So let's wait, Anil. Once the session is over, please be online. We will discuss with the TAs. Okay. So the TAs, please be online after the session is over. You be on the online meeting. Don't leave the meeting. Okay. Let's see.
Okay, sir. Okay.
So far 81 students have joined actually. So let's wait for another couple of minutes. 35 we will start. No matter how many joins and all. Can we start today?
Yes, sir.
Yes, sir.
Yeah, can we start, right? Yeah, good afternoon, all students. Today, our first experiment as a part of our mechanical measurements lab. So, as we have already seen the cycle 1, the first experiment is air velocity calibration using hot wire anemometer and pitot tube. Yes. So the same experiment we are going to do today. So first let us understand the very background of carrying out this experiment. The very aim of this experiment is to actually calibrate a hot wire anemometer. As you all remember, if at all you can remember, hot wire anemometer is basically used to measure the velocity of the flow, the local velocity of the flow. It's not the average velocity. Suppose there is a pipe and we want to measure at any particular location, that is where you'll actually find out the velocity of the flow. All right. So it is very, very precise instrument, and we can measure this with this instrument, how the velocity and all. We will come back to what is the principle, working principle and all. Just very briefly, I will focus on how we calculate the hot wire anemometer. Using hot wire anemometer, how do we calculate the velocity of the flow? Very briefly we will discuss. But time and again, the problem that comes with the anemometer is every time you want to use an anemometer, if you come to the formula, you can see over here the velocity is equivalent to I square R, where I is the current and R is the resistance of the wire, divided by A square minus B divided by the density of the flow. Okay, this is rho is your density of the flow, and you have two constants. If you see here, you have two constants. One is basically your A square, and A and B. Now what is A over here and what is B over here? These are two constants. Okay, so these two constants, they will be majorly found out. They can be found out by doing a calibration work. Okay, so that those constants depends on the how do you how close the instrument is able to measure, or how precise the measurement is the anemometer is able to measure. So for that, what you need to do is you need to find out what is the error associated with the hardware anemometer compared to the actual measurement. Okay, so for that, what you need to do, you need to do a calibration experiment. For that, you need to have a pipe around a pipe flow with the same experimental conditions like ambient air and all. So with that, what you do is first you measure the velocity of the flow at the same location by means of a standard instrument, standard velocity measurement instrument. Once you find out the standard velocity measurement instrument, you will use the hardware anemometer, and together at the same conditions, because that instrument should be able to provide, or the pipe line should be able to provide a proper or precise velocity of the flow. It should be controlled amount of flow should be flowing through the pipe. Okay, so you need to have a basic standard calibration setup to do this. Okay, that's why anemometer is very costly. If at all you are going for 3-wire or 2-wire, it ranges around from 8 lakhs to 15 lakhs or 20 lakhs. So very costly instrument if at all you are measuring the turbulence and all. So if at all you are using for a one-dimensional flow measurement or velocity measurement, it can be, you can get it around 20 to 60,000 range. In that range you will get, depending on your precision, you will be able to get. But our main aim is, you can see over here you have a hardware anemometer, which is, this one is basically one dimensional, which comes around 22 to 60,000. You can see there is an opening over here, right? I hope you are able to see this, right? You are seeing an opening over here, exactly here. So this opening is basically is kept in a place where you want to find the measurement, and there is a small wire which is connected, and this antenna kind of a thing can be extended, the stereoscopic stand we call it as. So it can be extended to whatever distance, and the digital value will directly come over here. The velocity values can directly come over here. So that is basically your standard one-dimensional flow conditions. If you are measuring, that is longitudinal velocity, if at all you are finding. So this is the instrument that we are using for velocity measurement. And now, as I said to you, that we want to calibrate this first. This is directly you will get the measurement, but every time you have to ensure that what is your A and B values, your constant values, what are those values you have to give if you go for precise measurement. Here you don't need to give, but when you go for precise measurements, you should be able to input those things so that your values are correct. So in such a case, you need to find out what is your A and what is your B. So every time when you are using anemometer for research purpose or for your experimental purpose, the best thing that you can do is you have to first calibrate it with a standard instrument where it can provide or facilitate a uniform or well controlled amount of flow with controlled flow, and a standard velocity measuring instrument which can measure the velocity accurately. So then we will compare both of them, and then, so the same procedure we are doing in this particular experiment today. Okay, any questions? So this is what we are going to do. So one of the standard velocity measure instrument that we are using is a hot wire anemometer. So we will see how this hot wire anemometer will be working first, and then you can go for hot wire anemometer. First we'll see how petard static tube will work, and then we will go to hot wire anemometer, how it works. Okay. So now you could see here there is a velocity there is some velocity through the pipeline. So we are seeing some flow is happening over here. So at any location, if the particle, it has an energy, it consists of some energy, right? So that energy we call it as stagnation pressure. When it is at a standard condition, it will have the total energy is nothing but its stagnation pressure. Now when it is flowing over here, if you put a piezometer like this, some of the liquid will rise over here. That means when it is at static condition, what is the pressure that is having, what is the energy that is having, is basically your static pressure. When it is not moving, when the fluid is at static. So at this position, what is happening? There is no slip boundary condition. So therefore, you will have only static pressure. And now you are putting a bent tube like this, 90 degrees at a location at which is access to the flow. So the flow that will enter into the pipe, and after this certain period of movement, it takes a 90 degrees turn. That means the velocity is completely converted into pressure energy. According to Bernoulli's equation, we have pressure energies, kinetic energy and potential energy. So now since the level of the flow here and here are same, so the whatever the flow that coming inside, its total velocity is also converted into total pressure. So there you can see that there is an increase in the pressure with this particular tube. Okay, so this tube will have an extra pressure which we call it as dynamic pressure, and the total sum of it is nothing but the energy possessed by the water molecule at this point. So we are considering two things here. We are just looking at two things. Sorry, we are considering at two things. Just a moment. Okay, so now what we are trying to do is we are applying our Bernoulli's principle over here. And what are the assumptions of Bernoulli's principle?
Steady state one-dimensional incompressible fluid.
What can you what is it?
Do you know
Fluids and incompressible.
when the water particle enters?
Yes.
Fluids are incompressible and the velocity is one-dimensional.
Exactly. So that is what we will look at, right? So now what we are trying to do is we have a few conditions that are there with assumptions that are there with Bernoulli's expression. So if you don't consider them, we will have some losses also. Okay. So how we write the Bernoulli's expression? The pressure energy plus kinetic energy plus the potential energy is constant for a fluid which is not having any rotation circulations. It should not have no friction losses, and it should be incompressible in nature. So these are the three conditions or assumptions which we do before taking the Bernoulli's principle into account. So when I apply the Bernoulli's principle here at 2 points, for example, at point 1 and point 2, okay, so since they are at the same line, your potential energy is gone. You are writing the pressure head, velocity head, and the potential head is equivalent to pressure head at 2, velocity head at 2, and Z2. The total energy at a particular point remains constant, but from here to here, there may be interchangeability of energy that may happen. That is what the principle says. The total energy, that means this total energy at 1 and 2 are same. That means if the summation of these, let us say pressure energy is 10, velocity is 10, and Z1 is 10. So total energy is 30. So at this point also, the total energy is 30 only, but it may be 10, the pressure energy may be 10 here, it may be 5 here, but velocity is 10 here, it may be 15 here. So there is a change in the energies from one form to another form, but the total energy remains constant. That is what this particular equation will tell you. So when you apply this, you see that the line, the potential energy remains constant because it is in the same line. So Z1 and Z2 will get cancelled out. And you can see here, whatever the whatever the flow that comes in it, this total energy of the velocity head is completely converting into pressure energy, right? It will be completely converting into stagnation pressure, P2. So this total thing will be, because the velocity becomes 0 at this line, so Vt is going to be 0. So P2 by rho g, whatever the energy, is nothing but your total energy that is associated with this particle, right? So now P1 by rho g plus V1 square by 2g is equivalent to the stagnation pressure. That is what you can see over here. So the same equations, if I write down, that is what you will be seeing, right? Velocity becomes 0, Z1 and Z2 will become 0. So the leftover thing is like P1, you can see P1 plus rho V square by 2, Gg will get cancelled, V square by 2 is equivalent to P2, which is the stagnation pressure over here. So now from this you will be able to find out what is the velocity of this particular equation, right? P2 minus P1 by rho, okay, and so under square root will give you the velocity head, what we call it. Okay, so that is what we are going to do. That's how we find out this. So the essential thing here is we don't have too many frictional losses, so this will be more or less, we take it as a standard pressure. Okay, we are assuming that it to be standard for measuring the velocity of the flow. Where the applications you predominantly will see in flow measurements, especially in aeronautical things, you will be looking at pitot static tube. While flights and all, for measuring the pressures and all or velocities, they use this pitot static tube under the left wing of the aeroplane, if you see that. So you can search and you can find out the applications of this pitot static tube over there. Okay, so this is the total working principle of the pitot static tube. And we also, I'm giving you here what is the design perspective of having a pitot static tube. You can see there are the top of the piezometer and the single pitot tube together is called as pitot static tube. Initially, whatever the 90 degrees bent tube, we call it as pitot tube. But now here, whatever we are using, it is basically having holes on top of it, so that the flow that comes in will give you this particular part, which is next to the main tubelet, main inlet, gives you your static pressure, and the rise of this will give you the total pressure or the stagnation pressure. From that you'll be able to find out the dynamic pressure or velocity of the flow. So this is basically about the pitot static tube. Now coming to the working principle of hot wire anemometer, we have hot wire anemometer that we can carry out this we can measure the velocity of the flow with the help of an anemometer by using two methods. One is called the constant current method, another one is called the constant temperature method. Both you know, right? You can see over here there is a pipe through which the gas is flowing. We have a Wheatstone bridge circuit. I assume that you know how this Wheatstone bridge circuit will be, and there is a rheostat for changing the resistance of the circuit and the battery for supplying the power. The galvanometer is provided here to provide the measure of the current that is flowing inside the circuit. So in general, when you have constant current method, okay, that means whatever the supply current that you are sending it through the circuit is constant. You are not varying it. Okay, so there is a filament over here which is connected to the resistance 4, and we have this 3 resistance, and you know the resistance, the ratios of the resistance should be same. R1 by R2 is equivalent to R3 by R4. So here it is like a symmetry over the x-axis. So R1 by R2 is equivalent to R3 by R4. One of the R3 is connected to, for example, is connected to this particular wirelet here, R1, R2, R3, R4. So based on that, you write the ratios. So when the flow is flowing over the small filament, okay, small wire, what happens is the temperature of this wire is reduced, because initially we send some current through it. Okay, before the gas flow, we are sending some current through it, such that the galvanometer shows 0 value. That means the resistance ratio across the symmetry becomes equal. R1 by R2 or R, depending on how you are, which one is your R1 and R2, R3, R4, your ratios of these resistors, okay, they should be the same. The ratios of this resistance should be same. So once it is achieved, the galvanometer will show you a 0 value. Okay, so for a particular amount of current flow. Now when you send the gas or some flow over it, because of its velocity, because of its low temperature, some of the heat is being taken out from this wire. Therefore, the temperature of the wire is reduced, and when the temperature of the wire is reduced, you will have what? You will have a resistance reduction. When resistance is reduction, you could see that there is some change in the current. So this change in the current is proportional to the velocity of the flow. So therefore, from this principle, you'll be able to evaluate the flow of the velocity of the flow. Right. This is one of the method called as constant current method, where your input current is not being changed, but the change in the resistance is considered for measuring the velocity of the flow, which is flowing over the anemometer sensor or wire. The second one is the constant temperature method, wherein the same principles are being used. What is the difference thing here is, here because of the temperature, because of the flow, the temperature of this resistor is reduced, therefore the resistance is reduced by suitably adjusting the rheostat provided over here. So the resistance is again bring back to the same value. So if the balance, the ratios of the resistance are balanced such that your G will be brought to the same value. So therefore your temperature, the current, when your resistor rheostat is changed, means what? Your current is being altered. So therefore it brings back to the original position. Therefore the circuit whichever is having, it is maintained at the same temperature, the prior temperature, even after the flow is happening over there. Whatever is reduced, the temperature is reduced by sending an extra current through the circuit. We are making again it to be at the same temperature. So from this you will be able to find out the velocity of this particular flow. So these are the two methods generally we will be using. So the basic energy balance, if you do heat generated is equivalent to heat loss. From that we will be able to find I square energy is the heat that is being taken out, and this is the expression which we call it as King's law, which we use. So the velocity of the flow and the specific heat of the flow is what actually takes care of the amount of heat that is being absorbed from the filament. So those things are taken into care. So now the final expression is V, velocity of the flow, is equivalent to I square R, which is basically your current and resistance of the wire, and A and B you have to find out from the calibration curve, and your rho is your density. Okay, so now this particular phenomena is what we are trying to do. Okay, you are trying to assume the A and B values. Okay, if at all, how do you get the A and B value? Whatever the calibration curve that you get, okay, if you are writing it in the form of this form, in the form of an equation, then you will be able to find out A and B. If you write it like y is equal to mx plus c, a linear profile, you may not be able to get directly this. Okay, right. So let us yeah.
But in that expression, sir, there should be the whole square of I square R by A, no?
I square R by
A. There should be the whole square of this.
I square R by yeah, that is the whole square. Correct. That is missing here. This is taken from internet. This is the whole square value. Correct. You are true.
Okay.
So I square R into A into by A. This will be, and this is your whole square. Okay, and minus B by rho. So it will be I square R. This should be square. This should not be there. Okay, correct. So this is how in general you do your experiment when you do your research or when you go for higher studies. This is how you have to first find the constants, and then you can suitably find out with the help of velocity. But what we have here is a single one-dimensional flow, one-dimensional hot wire anemometer. So it will give the values directly over here. Okay, it's not a 2-wire or 3-wire hot wire anemometer. So we are not following this. Directly the digital values will come over here. Okay, and we are also measuring the same flow. For the same flow, we are also measuring the velocity with the help of a pitot static tube, and both we are comparing and plotting a curve. That is what we are trying to do. Okay, so like this static pitot tube, what is its velocity? For that corresponding, what is your hot wire anemometer? That is what you are trying to find out. Okay, so now we will have a look at the particular experimental setup that we have in our college. Okay, what we are actually looking at, that we will see today. All right, is the voice audible?
Yes, sir.
This is the setup that we have in our laboratory. So this is the motor or the blower that we have, and this is the pipeline where we have, and this is the YouTube manometer which is connected to the.
Welcome everyone for this lab section. So in today's lab, what we are actually going to do is calibration of a anemometer. Okay. So in your report, it is given as hot wire anemometer, but what we are having here is a vein type anemometer. Vein type anemometer. So these are actually the blades in that. Okay. So while it is actually rotating, we can actually simply blow off and see. We can actually simply blow. You can actually see the vanes are actually rotating. Okay. So we are having the digital indicator over here. It is actually show you how much is actually the velocity. Once I blow this, you can actually see the velocity is actually going to increase. Okay. So the issue with this kind of instruments is that there are lots of uncertainty associated with this. Okay. So therefore, in this section, what we are actually going to do is we are going to calibrate this anemometer with something more labor. Okay. So we are actually having a vitrostatic tube inside. I will explain what it is. Okay. So we are actually calibrating the vein type anemometer against velocity measured from a vitrostatic tube. Okay. So let's see the experimental setup. So as I said, we are actually going to measure the velocity, or we are going to calibrate the velocity. Okay. So in order to do that, we are having a tube over here. Okay. So this tube is actually connected to the blower. So we will switch on this blower, and this blower is actually going to take it air from the outside, and it is actually going to push the air through this channel. Okay. So basically you are actually going to get a flow through this channel. So what we are actually trying to do is we are actually trying to measure the velocity of the flow. So obviously with the vein type anemometer, what we can actually do is we can actually keep it at the outside. Okay, keep it at the outside, and you can actually measure what is actually the velocity. Since we are actually keeping it touching the surface, you can actually say that whatever the velocity in the inside the tube, it is almost accurately we are actually measuring using the vein type anemometer. So in order to calibrate that, what we want is actually the actual velocity which is happening within the channel. Okay. So one assumption what we are actually taking here is, here the turbulence, the flow is actually in a turbulent mode. So therefore the velocity is almost a flat profile with it. Okay. So even if you are actually taking the velocity at the central portion, we are actually saying that is actually almost equal to the average velocity, which is we are actually measuring at the x. Okay. So what is actually the instrument for measuring the velocity of a flow within the channel? So that is actually vitrostatic tube. Okay. So you know the working principle for the vitrostatic tube. We are having a static tube over here. So once the flow getting inside that tube, it is going to get static or stagnant. So because of that, we are actually going to measure the difference between the stagnation pressure and the static pressure. And using the equation v is equal to root of 2gs, we are actually going to get the velocity. Okay. So for that, we are having a vitrostatic tube inside. Yeah. So this is actually the vitrostatic tube. It is actually connected to the manometer. Okay. So one end it is actually connected to the one leg of the manometer. So other end it is actually connected to the other end of the manometer. Okay. Yeah. Okay, so while switching it on, we can actually see that there is a deflection of water in both the legs. So that is actually your edge. So using this edge, you can actually calculate the velocity of the flow inside. Okay. So once we calculate the velocity, we are saying that is actually the actual velocity or the true value, and whatever we are calculating or measuring using the vein type is actually the measured value. So once we have the x's and y's, then you can actually do the calculations as we discussed in the introductory class. Okay. So let's start the experiment. So for starting, we have initially switched on the power. So now on the board itself, we are actually going to switch it on. Okay. So we have actually switched on. So this is actually a regulator. It is actually going to control the voltage supplied to the blower. Okay. So once you control this, you can actually control the blower, which in turn actually going to control the flow rate and therefore the velocity. So our intention is that when you are actually going for a calibration, you need at least 6 to 8 readings. It is better to have 8 readings. So at least 6 readings you should be having. Okay. So that's why there is a regulator. And if you are actually varying the voltage or varying the regulator, then ineffectively varying the voltage to the blower and ineffectively varying the velocity. Okay. So what you have to do is, or what we are actually going to do for you is, we are actually going to show you how to take different velocity measurements. Okay. So let's start. So we are actually going to start the blower now. Okay. Yeah. So now it is actually being started. You can actually see it from the deflection. Okay. You can see it from the deflection over here. See. So we are having some values. Okay. So this is actually the H we want. This is actually going to give us the velocity from the pitot-static. So now coming to the vane type anemometer, here you can see there is an arrow mark with it. Okay, so here there is an arrow mark. Okay, arrow mark within the vane type. So that is actually the direction of the flow. So the arrow mark is actually shown like this. So we have to keep our vane type anemometer like this. Okay. So if you are actually going to do it out here, whether we are actually going to get the same velocity, it is not, because already the velocity or the air is actually spread. So whatever the velocity we are measuring will be actually wrong. So we have to measure it right at the exit. Okay, so before the flow is going to spread, we have to measure it. Now you measure what is actually the velocity. Yeah, so it is fluctuating somewhere around 20. We can actually say the velocity is actually 20 meter per second. Okay. So we have taken one reading. So now we are actually going to increase the flow rate. So you can see that the deflections actually increase. Okay, so now you can actually see it is reflecting somewhere around 23.5. Okay, so likewise, you have to take some minimum 6 readings. Okay? And once you have these 6 readings, then you can actually do the calculation. Okay, so after taking all the readings, you have to switch it off. So for that, you have to again reduce the voltage to the blower, make it to 0, then switch off the set. Okay. Okay.
So any doubts up to this part? Yeah, go on. If you have anything, any questions, I'll be happy to take. So this is the procedure that we have to follow. We have to switch on the vanes. So for different speeds of the blow air, if you vary the regulator, it will give different flow rates. And then for each flow rate value, you will have a YouTube manometer reading. And from that, you carry out the manometric head H value you'll find out. And similarly, we are also finding the hot wear anemometer by placing exactly at the center of the flow in normal direction. And for different things, you will repeat the same thing. Tabulate the values, and we are assuming over here that the pitot tube is more accurate compared to the hot wear anemometer. Therefore, we are kind of using this for calibrating the hot wear anemometer. This experiment is. So what can you think of what can be the possible errors that may come in with the hot wear anemometer apart from the wire and all? What can be? I mean, there is no wire over here, but it's a vane type anemometer. It's not a hot wear anemometer. You can say that it is a.
But it's flow obstruction manometer, not flow obstruction manometer. So
which one is not flow obstruction? So for the vane to rotate, some of the energy will go to overcome the friction, isn't it? So some energy may go into it. Okay, over a period of time, that friction will tend to increase higher. So that can be one. There may be some breakage in the one of the impellers or the vanes. That also kind of give that actually varies the flow over the impellers, and therefore the rotation that is giving may not be correct. And the internal circuit over a period of time may not be working properly because the number of revolutions you are carrying, and that you are converting it into the velocity. So the major thing is we started this experiment with a hot wire anemometer where we are trying to find out the values of A and B, all right? But since we don't have the hot wire anemometer in working condition, we are taking the help of a vane type anemometer. And here what we are trying to do is we are trying to calibrate the vane type anemometer here, okay? You may ask, sir, why you are then talking about the hot wire? Because the principle is same. Suppose if you go for higher studies, and if at all you, the basic thing is when you are a thermal side, you were bound to measure the velocity as well as your temperatures. Sorry, you are bound to found the velocities of the flow, temperatures of the flow, and different properties, thermophysical properties. So the flow rates and all of that. So your basic understanding of this will help you to calibrate. You should understand that in experimentation, when you touch anything, first the question is to find the uncertainty of the measurement by the instrument. You have to find out that. If you are doing without doing, if you are not finding the uncertainty, or if you are not calibrating the instrument and you are using, your repeatability will be wrong. You will not get the same values repeated when you do it for the second time or third time, and people will always question your results. So with the aim that you should be able to understand that, I actually gave this. And these are the readings for two sections, for the two different sections. Section A, you follow these readings, right? And here it is section B. You can see here I have given manometer reading, and from this you have to find out the actual velocity. Okay, and this is the actual measured hot wire anemometer reading. While calculating the velocity from the pitot tube manometric reading, you have to go through the manual. Okay, there is certain things that are given. What is the manometric liquid that you have used? From that you have to find out your H, and that you have to use in the formula, velocity formula, which is square root of 2gh, and then find out this. Okay, so I've already put that in the folder. I think I shared the folder with you. Is it available with you? There is a lab folder that is being shared with you. Is there anyone?
Not shared, I think, sir. You shared the YouTube video. I mean, drive video.
Yeah, in the drive drive videos are being shared, but at the same time, another thing with the lab thing, it is not being shared. I will share it now. Okay, just now I will share that.
Only videos.
Just a minute. Share that manual. It's manual. I'm sharing you directly. Now I guess you will get it. Yeah. So this is the manual that you are getting. So use the expressions over here, whatever is here. Okay. Appropriately, you find out what is the velocity by the pitot static tube as well as pitot tube as well as the anemometer. All right. I hope the experiment is clear. Any questions?
Sir, one
Yeah.
doubt. We are given readings, no, sir. Those are of taken from hot wire anemometer
No.
experiment or
They are taken vane type. They are from the vane type anemometer.
So both have the same type of constant, sir.
No, here there is no constant. No, it is basically your electrical circuit.
Just
The rotations,
we
the
have
number of
calibrate.
rotations, you are actually trying to connect with the velocity of the flow. Okay, you are trying to relate those two expressions. So here the constants will not be there. Whereas in a hot wire anemometer, since the expression we use that, there are two constants. So if at all there is that hardware anemometer, we have to find that A and B. For example, if you want to use the hardware anemometer, there will be a calibration setup. That's why I told you at the start itself that setup is very costly, 15 lakhs, 20 lakhs it will be, because there will be a calibration setup that they will give with along with it. So before using that, you have a standard setup where it provides, if you want 2 meter cube per second amount of velocity of volume flow rate, it will directly provide that. 3, it will well controlled amount of fluid will come out. So that you can measure with this with this anemometer, you can put at the end and you can correlate or calibrate what is the value, exact value of the flow, what it is showing, and from that you get a curve. From that curve you will try to find out the constant values. Once you get the constant values, you will take that and put before any instrument or any flow conditions where whose velocity is not known. Already we have calibrated it, it's working fine, we know the A and B, so therefore directly you can put A and B, and I value, current value and R value will be knowing, so automatically you'll be finding out the velocity. Okay, so the I and R values are also not required. A and B you have to give as an input. The other things that automatically they will calculate. The instrumentation will help us to calculate what is the current and what is the resistance. Those values will be automatically done. Only you have to give input as A and B. What are the values of A and B? Once you give that, it will automatically take. Understand?
So yes, sir. So theory should be written for hardware anemometer and procedure and calculation should be done for.
If you want, you can write it for a vein type anemometer. You decide on it. So the experiment is started for hardware anemometer. You can write it for vein type anemometer also.
Okay, sir.
But what my suggestion is, please don't put whatever is there directly into this. Okay.
Yes, sir.
It's almost everything is there. If you copy that, what is the point actually? So try to understand and try to put some information into this along with it. Okay, some information if at all is finding, you put it and submit by next Wednesday. Okay, so that we will have time for calculation and all, correction and all. Okay, so the point is there will be marks for neat writing of the record. Okay, 1 or 2 marks I will give for neat presentation of it. And don't write it as a rough kind of a thing. Okay, calculations you be specific, very neatly you do the calculation. There is not much to vary in this, but timely submission is also important. This time I am not going to allow any delay in the submission of the records, just to get some variation in the grades, nothing else. I won't have anything in mind. My only intention is to get some variation in the grades. That's it. Yes. Any more questions? I'll be happy to take.
Sir, for fan type anemometers, what type of gases can be like used to be measured? So
Which
like
one?
for air, sir, for fan type anemometer, sir, which was shown in the
Anything which can rotate. But the problem is, suppose if it is more contaminated, the issues are like this. If the flow that is having more amount of particles which get stuck onto the impeller or blades or the vanes, then the rotations will be different, no? Because of the sticking of these materials onto the top of the surface of it. So any gas which is pure can be used. Anything which can impart some momentum can be used. There's absolutely nothing. But if you use for some oil flow and all, for example, okay, so there what happens is like this is very basically this is for gas flow. We will generally use this vane type because these material. If you want to use it for liquid, what is the problem? You tell me. Liquid will have more density, and for more density fluid, if it gets up, it gives an impact. The chances of the blades to break will be more. If you want to give a sturdy or strong blades, the density of the blades will become more, and then the rotations will not be accurate. That means you will not be able to measure the lowest velocities. For the lowest, like 0.1, 0.2 also, it should be able to rotate, and that we should be able to correlate with the flow velocity, correct? So these are the problems. So therefore, you have to think that it can be used mostly for the gas flows, and the care that we should be taking is it should not be having too many dust particles inside the flow. It should be filtered kind of a thing so that it can measure any flow velocity. Clear? Is it clear?
Yes, sir.
Yeah.
Sir, we got only manual link, sir. We are
I
not
said
getting values.
values I have not sent. Whatever values
Okay.
I have given, you know, that PPT I will share so that from the PPT you will take.
Okay, sir.
Anything more? Please try to put some information into that. So which one you'll write type vein type anemometer instead of
Yes, sir. Vein type.
so I'm telling you to write vein type anemometer, get some information about vein type anemometer and how it works, kind of working principle kind of a thing you write down, and from that you draw the graph and how it is varying. Please put it. Okay, and after the first cycle we will have one quiz where we have this marks bifurcation and all we can get, but timely I'm setting you the time. I will give you the link so that around that link you have to submit your records through that link by that time so that it will become easy. I think last time if you scan your records without a background, okay, if you take out the background, I think the size of the file will be lesser only. So please try to submit through the LMS, okay, so that for us to correct it also becomes equal. If you have any other issues, you please let me know through the CRs, okay, by tomorrow. Okay, so any further questions, or if you want, I can stop the session for today. Any questions if everything is clear? Can I?
Yes, sir.
So what I'll do over here is I will take the okay, I will send this, don't worry. All right, these marks I will this PPT itself I will put it in the same folder and share with you. Okay, so can I stop the recording?
Yes,
And
sir.
no questions.
Yes, sir.
If you have no questions, I will stop for today. Okay.
Sir, also, can you take from WebEx from tomorrow, sir? Like, actually, Google Meet have removed the free
Exactly.
recording
Yeah,
option.
yeah. I say that. They're asking price for it. Now they made sure that everyone is addicted to it, and now they are taking money for that. Because they also have their problems. The space requirement will be greater, no, with the recording and all. They can,
Actually, ours was the licensed one only, sir, enterprise version.
but
But since we did not upgrade, they
Mhm.
removed for that.
I don't know. But today only it has the problem has come, no?
Yes, sir.
Yeah. So no problem. So we'll switch ourselves to WebEx. It's okay. It's good actually. But the only problem is you have data issues and all. That's why we are actually taking the help of Google Meet. Now we will switch out from Google Meet. We will go from that. All right. Yeah.
Yes.
So I'm stopping sharing, and so please, apart from the TS, you please leave the session. I just want to have a word with the
Thank you, sir.
TS. Yeah. Thank you. This is fine, right, guys? This much time only it will take. Okay, even lesser than this it will take because the experiments will not take too much of time and all. So spend the rest of the time for making the record and all, and timely submission is what I'm expecting from you. This time is
Yes.
fine, right? This much of
Yes,
time.
yes.
No quarrel,
Yes,
no
sir.
comments that the time is less and all, right? I expect no such things from you. Okay, right.
Yes.
If you have any suggestions, you please let me know through your CRs to improve the lab and all. If you are happy with that, you let me know that. If you have any criticism or comments on that also, I'll try to imbibe and make it more useful to you. Okay, sure, it's totally fine, sir. No problem. Okay, sure. Thank you. Thanks for the comment. All right, please leave all of this except the TS of the scripts.